Hey guys, it's Nivi and this is my Physics of Extreme Sports with Ropes lab. The goal of this lab was to analyze on tracker the motion of a spring mass that swings in an arc while oscillating, then use V-idle to predict the motion while keeping in mind the energy principles and Newton's second law. The result was that the predicted motion was similar to the observed, and the principles were supported by the spring mass system. Here's my tracker video. I have the spring mass system pointing downwards on the y-axis. I also calibrated the length to 0.7 meters, and from the table I can see the x and y positions of the system at the given times. I also plotted the x and y positions that I got from tracker on a graph to help me visualize and make my CSV file that I later needed. We used two principles, Newton's second law, which states that the acceleration of an object is dependent upon the net force and the mass of the object. We used it to find the spring's new velocity and its new position. We also use the energy principle, which states that a change in energy equals a change in kinetic energy plus a change in spring potential energy plus a change in gravitational potential energy. Here are my initial conditions. The ball's mass was 0.402 kilograms. The x and y initial positions at time of rest is shown here. And since it started out from rest, velocity is 0. The code runs the x and y positions from my tracker CSV file right here. Here's my work shown for the time step between one oscillation and the spring constant and the change in stretch relax length of the spring. This code calculates the length of the spring as time goes by. L hat tells the spring direction, while S shows the stretch or compression of the spring, and it is used to compute the spring energy and force. I also coded for the formulas of kinetic gravitational potential and spring potential energy right here. Here's my while loop showing the net interactions. Fgrav only considers the y component because that is the only axis it is interacting with. For F-spring, remember the a stretch means the S is less than 0, while a compression means the S is greater than 0. Fnet is the spring and the gravitational force combined, and Newton's second law is used to find the spring's updated position and velocity. Next, as the position of the spring changes, so does the spring stretch and compressions. This code is used to update the visual model. At each time interval, the kinetic energy, gravitational potential energy, and the spring potential energy is updated, which are then plotted to show the energy changes for each time. Here's my code to plot the different changes in energy. This part was used to compare the x and y positions from my predicted model to the actual model analyzed on tracker. Now let's run the code. As you can see, the red ball is the position data from tracker and the blue ball is the predicted model from my code. You can see they are very similar in pattern, but not an exact match. That is due to roundoff error, and it is hard to pick the exact point with my point of mass, so this is where my errors may have come from. The blue arrow is the spring force, and the black arrow is the gravitational force. And the graph also shows how the blue line, which is my predicted model, very similarly matches the red line. Okay, so the blue line in this graph shows the kinetic energy, while the red line is the spring potential energy, and the green line is the potential gravitational energy. And the sum of it all, which is shown in yellow, is 0. Therefore, we know the energy principle is satisfied and energy is conserved, and we chose everything to be in our system. What does it mean? For your model system, is the energy principle satisfied? Yes, it is. The work done by our surroundings does equal the change in energy, and since there is nothing in our surroundings, since the Earth, the spring, and the masses in the system, therefore the change in energy should be 0, and that is shown by the yellow line, and it does indeed equal 0. The oscillations for x and y are shown here. The period for x is 1.7 seconds, and the period for y is 1.52 seconds. The two differ by about 0.18 seconds. They differ because the equation to find both differ in value. For instance, the y position time period is based on mass and stiffness, while the x position time period is based on gravity and length. So it takes a longer time to move in the x position or x direction than the y direction. It moves in a pendulum motion for x component and spring motion for y component.